Hi my friends. Today we continue with the discussion about design accelerator, focusing on power transmission. We discussed about disk cam, and now we make an approach to the other kind of power transmission. Actually, we discussed about SPUR gear, BEVEL gear, worm gear, V-belt, synchronous belt, roller chains, key placed on a shaft, parallel splines, and O-rings. Let's start. We create an assembly based on this template, and we start with the SPUR gear. In order to have some objects where we place this assembly, we place two shafts. One is placed grounded at origin and the other is anywhere. We apply constraints between these two, and we use work planes from the origin. They must be aligned on this direction, apply, and place at a certain distance, 120, on the other direction, apply, and they must be at the same level up. Then we go to design accelerator and activate SPUR gear from these three kinds of gears. We press and keep pressed the key control to get the default settings. Then we select a design guide module. You have to know what you do here. Yes, when you intend to design a SPUR gear, you have all the data on the table. I use some data, but you have all the freedom to select other data. I place a helix angle of 12, a number of teeth from the first wheel, which will be here. Let's show where it will be here, and starting from up, but the other direction. Yes, this will be the first wheel. The other number of teeth is 51, and the cylindrical face is this. We take a look of the settings here. 1 kilowatt is the power, 1000 RPM, and let's see also this more type of load calculation. Okay, and to the other number of teeth. Okay, the input type. Let's see what happens if we apply calculate. Everything is okay. As you can see here, calculation indicates design compliance. Let's see how it looks, this SPUR gear. Okay, we save files in the work directory, and the SPUR gear is presented. When you rotate one wheel, you will see the movement of the other. Why? Because here is a new object in the browser which has the specific mark here of flexible. Yes, this is flexible. Good. Now you can refine every wheel. Double click to obtain the spur gear, double click to get access to the wheel, to one wheel. We know the diameter of the shaft is 25, so we create a point on a sketch to apply a hole in that point of 25. Okay. Then we can apply a new sketch like this circle of 40, another one of 140, finish sketch, then extrude of this, cut 3 millimeters. Okay. Fillet, fillet. Okay. And then let's change the aspect in the new extrusion to be very nice. This is how I like them. And we go back. If you refine more, you can obtain such a beautiful presentation. Next is the worm gear. We start with the same template. We place the first shaft grounded and the other here. Then we constrain them by applying an offset between the YZ planes of 125, but in the other direction minus. Apply, then an angle of first solution between XZ at 90 degrees. Apply, axis Z of the second to be placed from this plane, not an angle, a mate at a distance of minus 150 divided by 2. Apply, and then this plane with the axis Z of the other object to be also at minus 150 divided by 2. Okay, what we have now? We have a positioning of the two shafts at a 90 degrees and with a distance between them. Again, we go to the design, but we select now the worm gear. We have to save it as an assembly, yes, and we select some data here. They are really the default data in all. Let's select the cylindrical face on both. Then we have a solution here. You see, always you have a preview, and you can adapt your data to the requested data by identifying these variables of worm gear, or worm. This is the worm, and this is the worm gear. All the data are okay, so we ask for calculation. Let's see the power. 0.1 kilowatt. Okay, calculate. Nothing is here, so nothing read. So we see that the calculation indicates design compliance. Let's see how it looks. Okay, this is how it looks, and again flexible is here, so we can rotate the worm, and we see the worm gear rotating as well. Because there is no friction, we can rotate the worm gear, and we obtain this. We can edit, always we can edit designing objects and sub-assemblies. For instance, to change the number of threads of the worm, yes, instead of 1 I place 3. Calculate, okay, okay, and now you see another situation. There are 3 starting coils here. This is 1, this is the second, this is the third, which makes another ratio of rotation between the two. We can refine the assembly to look better. Next is bevel gear. We start with the 2 shafts. One is grounded at origin, and the other is near it. We apply constraints between the work entities. The first is XZ, coincident with XZ. They are overlapped, no problem. Then the YZ and the axis Z are to be at an angle, not 90, but minus 27. Apply. We place this axis on this point, then with mate. The axis with the center of the superior circle. Apply. What we have here? We have this situation. We can move only along its axis the second shaft. We constrain this face to be at a distance from the center of 50. Okay, F6. This is the starting situation. You see they are coplanar. Yes? The two are coplanar. This is the condition for the bevel gears. We go to design, we activate bevel gear, we save this new assembly, and then we press Ctrl and we apply click on the bevel gear to obtain the default setting. Our data are starting with selecting the cylindrical face, the end face, and the same for the other axis. 19 teeth and 67 to the other. 67, but I select this, double click, and I write here 67. Yes, now is 57. Delete 67. Now they are combined together. We apply calculate and OK. This is the result. You see, they are working together very nice. You can obtain, as always, a report with all the data. I want to not forget this. Edit using Design Accelerator, and you apply this results, and you obtain this all beautiful set of data, which can be saved as HTML file by using Save As. Yes. Good. You can create refined aspect, and of course you can create a drawing. All you have to do is to open the drawing and to apply a base and then a projection. Okay. You can obtain also another projection like this one to show the whole construction. Yes, very nice. Or as a picture, not a drawing. Now the V-belts. We start by creating an assembly, and then directly we go to the V-belts, Control click, save, And now I select a plane to have the first view of the future V-belt. We accept this selection and we'll see what is it about. Then directly here we modify the diameter to 50 of this pulley, and then we enlarge this to 180. The length of the belt is 872. You see that we have steps. Yes. Why? Because the distance between the axis and the length of the belt are combined. Okay, we want to apply to, let's make a calculation for what data, 0 kilowatts. It shows design compliance, of course, but we want to place here another value, 2 kilowatts, yes, and 3000 rotations per minute, RPM. What now? Calculate. Oh, not good. Here is mentioned insufficient number of belts. Let's multiply them. We place 4. You see the new situation? 4. Calculate the same. We place here 7. Calculation. Okay, 7 belts. How does it look? Okay, it looks as you can see, yes, but 7 belts is too great number. We add it by using design accelerator, and we change the section from 10 din Deutsche Industrie Normen to din 13, not 10 but 13, yes, another section, a greater one. So I suppose we can reduce this to say 5. Calculate, okay. What about 4? Calculate, no good, yes. We have to place here 5 to have the compliance with 2 kilowatts and 3000 RPM. Calculate, this is okay. Okay, you see how it looks. If you edit the wheels, you can obtain something like this. If you want to rotate, you see that it is not possible. Why? Because they are not flexible. We apply flexible and we can rotate. You see here, yes, and the result is here. You see, both are rotating. Good. Synchronous belts. We start as always, design, control synchronous belts, save, OK, F6, the plane is this one, and now we see the first presentation. We add a pulley by clicking here and selecting double flanged, and you see we can move this to respect a specific length of the belt. Of course, you can also add a flat pulley, and you have to change the motion direction if you want to use it in the other way on the back of the belt. Yes, I place this here. You see, only this can be moved and to change the length of the belt. Yes, you can modify the diameter of wheels. Oh, this is minimum. Okay, let's suppose this is what we want to have. You can understand these things, of course. Calculate. This is a smaller diameter and this is not good. I suppose this one is with a smaller diameter, or this one. Okay, now is okay. Okay, let's see how it looks. You see, they have teeth. You can edit them to look better. Now the same situation, you cannot rotate this until you not change to flexible. Now you can change and you see the results. Yes, everything works okay. F6, we select a plane, this one, and we can see the default situation. We can change the distance, you see, in steps, the diameter, and always the step of the roller is respected, of course. Calculation 0.1 kilowatts, 0.25 for us to be more interesting, and then calculate. Not good. Exceeded permissible pressure in chain bearing area. let's modify by changing the diameter like this, and again calculate. You have to try a little and you find your desired result. How it looks, okay. F6, you see how it looks, but it has no flexibility. I apply flexible and I can make movements, correlated rotation accordingly that to wheels. The next challenge is to apply is to place a shaft grounded at origin, because we want to apply here a key. Yes, we go to design, we select key, this is key, but control key to have the default settings. And now we select what objects to generate. Now are selected all. The key, the channel in the shaft, and the channel in the hub. We don't have here a hub. We deselect this. Yes. Now we select references. This is the first, the end is the other, and we already have the future key. It is suitable to this diameter, be sure of this. We only select the length. We want a length of 28, this is 28, and 7 millimeters here. This is to be written somewhere. Not here. Well, let me move it approximately 770. Okay, we select power 0.25 at 3000 RPM, and we calculate. Since we don't have anything here, it means that the design compliance is respected. Okay, okay, and we have the key placed on the shaft. Yes, that's all. Next and last are parallel splines and O-ring. We create an assembly. We place a shaft grounded at origin, escape, and then we go directly to the parallel splines, but you have to know that there is also involute splines. I keep Control pressed and I select this, I save, OK. Reference for the parallel splines is this cylindrical face. The other reference is this to the left, and we have to select which object to generate, shaft or hub. A shaft. We deselect this. Yes. Good. Now I want to enlarge this to have 56. Okay, that's okay. Okay, we can add it, of course, to change the power. For instance, 0.25. Calculate. Design compliance. Okay. Good. To the same shaft, we want to apply an O-ring. We select O-ring and we have to select what kind of O-ring we want to place there. And we want this one, hydraulic external. Okay. Surface. This is the surface. Reference is this. But inside at a distance of 8 millimeters from the reference. Okay. Okay. And now you have suitable O-ring. Well, that's all for today. Thanks for watching. Bye bye.